So from your email, you said that you need to know more about cleavage, but to understand cleavage better. Cleavage is, I'll give you the definition I gave in class and then I'll explain it, okay? Cleavage is the manner in which a mineral breaks based upon its internal atomic structure. What does that mean? Every mineral is a solid configuration of atomic bonds. Some atomic bonds come together and make a gas. Some atomic bonds come together and make a liquid. Some atomic bonds come together and make a solid. Well, when those bonds form a solid crystalline structure, it makes a mineral. Okay? Now, not all bonds are going to be equally strong as the rest. Some will be weaker than others, right? For example, if I were to take, what's a good example here? If I were to take a deck of cards, okay, and then if I were to just like hold it right here in my hand and then try and chop it like this, it's not going to chop very easily, right? But if I were to try and chop it like this, it would instantly fall apart along all of the planes between each one of those decks of cards, okay? You can think of it like that, where there is a lot less holding all of those cards together this way along the plane of the orientation of those cards than there is this way, where trying to chop it like this is going against that those planes, okay, between the cards. I'm going against the material instead of with it. So you can think of cleavage like that in a mineral, okay? So there are different types of mineral cleavage that you can see, okay? And we differentiate them from each other based on how many cleavage planes there are, so how many planes of weakness, and at what angle those intersect each other at, okay? So one plane of cleavage will look like this, where your mineral just falls apart like that, like in sheets, like that deck of cards I mentioned earlier, or like the pages of a book. They separate from each other in sheets like this. Now, when there's only one plane of cleavage going through your whole mineral, there's no angle, okay? They don't approach each other at any particular angle because they are all going in the same direction, okay? So in this case, you would just say one plane of cleavage. You may also see that described as basal cleavage, okay? When you have two planes of cleavage or more, that's when that angle comes into be a little bit more important. So two planes of cleavage is going to look something like this, okay? Where I have two planes. Let me try and angle this better here for the camera. Two planes. But wait, you say, there are four sides here. How do I know that there are two planes? Well, because this plane, or that side and that side, are the same plane. They are parallel to each other, making them the same plane. That plane of weakness is the same as this plane of weakness. They are not unique from each other, but they are unique from this one. This and that are the same plane. This and that are the same plane. Okay? Now, these look flat, but I have fracture written there to show you that, or to show anyone that's looking at this closely, that those are not supposed to be flat surfaces. These are the only flat surfaces on these models I made. Okay? So they break along those planes of cleavage, like so. And you would look at that and you would say, that's at about 90 degrees. Okay, so I would say for this, two planes at 90. What about two planes not at 90? It'll look something like this. Same thing as that first one. Fracture, fracture, flat, flat. But the angles between these cleavage planes are now not 90 degrees. So you can see that's an acute angle. And over here we have an obtuse angle. Still have these two parallel sides that represent one plane of cleavage, one and another one, but not at 90 degrees where they intersect. So this is two planes not at 90. Three planes at 90 is going to make a sort of box structure like this. Okay, so we have 1, 2, 3 planes. Okay, and they each have their own matching side, making this box shape. So 6 sides, but 3 unique planes. And they intercept each other at 90, right there, 90, right there, and 90, right here. So you would say 3 planes at 90 degrees. And when you break that mineral, it's going to break into smaller boxes following those 3 planes of cleavage. 3 planes not at 90 will look very similar to that box, but lopsided, like it kind of got squished or melted sideways, okay? A rhombohedron sort of shape is what we're talking about here, where we still have 1, 2, 3, I'm trying to do the size that you can see from the camera, okay? 1, 2, 3 planes of cleavage, okay? And they break not at 90 degrees to each other, right? Not at 90 degrees. Trying to not at 90 degrees. But, so you got 3 planes not at 90, and that's how you would describe this shape. Then we have, and this is the most complicated one I give you in this class, 4 planes of cleavage, okay? And when that happens, you'll get a shape like this, an octahedron sort of shape, where my mineral breaks there, 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 and there, okay? And so you're going to get the matching shapes on the opposite side. So that matches this. This matches that, so on and so forth. And so you get this sort of double pyramidal shape here, okay? This is an octahedron. So this is 4 planes of cleavage at not at 90 degrees. Okay. Commonly, if your mineral is too broken, you'll get great cleavage data, but not any crystal form data. Because remember, your crystal form is the shape that it forms as it's growing. So if my mineral is really broken, you probably won't see the original shape. But if it's not broken enough, you'll probably get the crystal shape without getting the cleavage. So you should always have one of the two, and in a few rare circumstances in the lab, you'll get both. I hope that this helped.